Okay, it's time for get started for the next second ACF webinar. Today we are going to have 4 speakers specialized in the area of 3D printing and construction automation, as announced. This is organized by Asian Concrete Federation, administered by Global Education Center for Engineers at Seoul National University, and also co-sponsored by American Concrete Institute, ACI. My name is Thomas Kang at Seoul National University. I'm the moderator of today's ACF webinar, and I'm very pleased to be part of this webinar, and also I'm going to participate in the panel discussion together with the speakers. We have some audience on site in Korea, and we have a lot of audience connected via Zoom. So there are many different audience in different areas, including Asia, Europe, and America continents, and Australia. So this is a truly global webinar. Here, ACF President Dong-Uk Choi is attending on site, so I'm happy to introduce. Okay, so he said he's here, but he's not gonna have a welcome speech because we almost it's almost time for the first presentation. First presentation will be made by Professor Sung-Gol Hong, my colleague in the same department at Seoul National University. Speech title is The Optimal Velocity of Extrusion Nozzle for 3D Concrete Printing. Professor Hong is a professor at Seoul National University. He graduated from Lehigh University, where he studied strut and tie models for the bar development and anchorage. He's a member of ACI, National Delegate of Korea for FIB, and a member of editorial board of Structural Concrete, which is a journal of FIB. He's an active member of FIB Working Party 4.2.1 on shear strengths. He's been working on both material engineering and structural application of UHPC and 3D printing technologies for almost 10 years. With that, I'd like to welcome Professor Hong for the first presentation. And if it's already, please, yeah. Thank you very much.
Good afternoon, everybody. I'd like to talk about the optimum velocity of the extrusion nozzle for 3D concrete printing. This time, I'm happy to give you some my research result in the ACF the special seminar. My name is Sung-Gol Hong from Seoul National University. My major interest in concrete technology is to develop some high performance concrete and 3D concrete printing and some functional material. Today I'd like to talk about the following contents for my presentation, from the background to the future research of 3D concrete printing. In these days, many interesting conferences already have been held. For example, digital concrete started almost 8 years ago. So I participate the second conference 2020 held by the Eindhoven University Technology in the Netherlands. The conference gave us a lot of interesting technology, 3D concrete printing. Also, many university center, for example, ETH in Switzerland, already produce very complicated decoration with the 3D concrete printing and together with the ordinary the reinforced concrete column. Another interesting is industrialized the factory using concrete printing technology in the Deutschland. They are producing the precast concrete element by the 3D concrete technology without the moldless the process. Very interesting industry for more the automatic the produce of the concrete element. For more larger construction by the 3D concrete printing, nowadays they are use the robotics with some vehicle. That means moving robotics, and also some the large scale of the gantry type 3D printing already used to produce the concrete the structure. The main problem in the control crafting construction, it is a stability problem. The stability is depending on orientation of the wall stacking. In first one is vertical printing, a very normal problem. It had it has some slope, that means tangential printing need more consideration how to control the stability. Another the interesting the printing skill on the curved surface, we need to print out to produce some curved loop of the curved shape of the concrete material. In this case, we need more complicated problem of stability of the wall. To solve the stability problem, we needed to paradigm shift from a normal the paradigm, so-called hardened concrete to the fresh concrete. That means we need to understanding of the rheology. That means what is viscosity of the fresh concrete, because during the 3D concrete printing, the concrete need time to harden. That means the hydration time is required to reach some strength, some the stiffness. So that means more complicated, more the detailed consideration of the concrete material rather than hardened concrete. So in the beginning of the concrete the printing technology, many people think about what is major challenge the people we applied the 3D concrete in the industry. So they listed 5 main problem. Number 1 is the stability problem. Number 2 is the workability. Number 3 is some deformation after extrusion. Also, we needed to how to control the setting time for fresh concrete. Finally, we needed to avoid the filament cracking around the corner. So people we start to discuss the stability problem as a main topic in this presentation. I'd like to talk about the rheology of the concrete. Rheology is very unfamiliar to ordinary the concrete man, concrete people, but it's for 3D concrete printing, we need to understand what is viscosity. Viscosity, it is expressed by the in terms of the shear rate and shear force, or kind of the dynamic property. So shear rate means just the deformation divided by the height in this diagram. So up to tau zero, that is a static behavior, just the no shear rate. After some this point, just the flow is begin. So flow is depending on the shear stress uh, against the shear rate. So the slope is is defined by the viscosity. If tau equals some point, that is called the Bingham plastic model. Tau equals 0 is a Newtonian model. Already we are familiar with the viscosity, the concept to explain the creep by the Kelvin-Voigt model. Also, we already know the Maxwell model to explain the stress relaxation. To measure the the viscosity of the fresh concrete, we applied some torque into the fresh concrete cylinder. So we measured the torque and the deformation. That means the twist angle. Then already some dimension is given. We plug in that result measured into this equation, so we can assess the viscosity of the fresh. So to apply the very important formula, also we assessed what is the optimum nozzle velocity. We need to know about the information the fresh concrete, such as the viscosity, also initial strength, also the initial stiffness. That means the Young's modulus. Also, how much increment as time is going, time, the function. So, uh, in addition to the viscosity, we need to measure the elastic modulus, elastic devolution by the time. So time is important parameter to get some strength and some the stiffness. So only we measure the viscosity, but tau equals strength. Tau's initial strength is increased by time. So we assume we apply the exponential function, or we assume the linear equation to get to assess the strength increment. Also, we needed to assess the stiffness, the elastic modulus. So from the shear modulus, then we applied this relationship, we get the Young's modulus. So from this equation, we can get some strength and stiffness evolution. So here is a typical strength and stiffness evolution of fresh concrete in terms of the exponential function with the ATHX. ATHX means seismograph. Seismography means some total uh, the representation of the evolution of the rheological material, usually the concrete. From viscosity and the initial strength, we need to how much the fresh concrete discharge at the extrusion nozzle. From left side, that means some inlet, the input of concrete under the pressure. Then some length of the pipe, we we assessed how much fresh concrete discharge depending on viscosity. Also, what kind of the concrete is the, the effect that this the concrete discharge. So here is a circular section of the pipe. So this is a center of the pipe. We have some prog flow, then some is a slope of the velocity profile expressed by the shear flow. So then what is the Q depending on the P? So P is the pressure input in the end of a pipe through some length. We expect some the discharge of the fresh concrete. So it's depending on some yield stress. In case of the conventional concrete, the yield stress is larger than the initial shear stress. So the the velocity profile in the extrusion nozzle, the shape of some prototype. So prog flow and the small the thickness is a lubrication layer. So velocity profile consists of two type of the profile, but self-consolidation concrete show the three different profile: the lubrication layer and the shear, the plug flow between two profile. We expect the shearing flow. So the different the profile of the velocity. So in the only prototype, that means prototype and the lubrication flow. That in this case we expect the delta P or Q is depending on the P, but we need to the initial the yield stress, and that means the lubricate the flow if the contribution. Another one only the prototype. This term is represent the plug type the discharge. How about the three different velocity case? That is the shear flow and the flow type, flow, and the lubrication slip. So we have a little bit complicate the expression between delta P and the Q. So here we have some complicate the relationship here. Then let's move the stability issue. So we just classify the two type of the shape of the wall. One is the cylindrical or shell type the wall. Another one is rectangular wall. That means just the plate type. These walls showed the similar the failure, the global buckling, also local buckling, and the yielding of the wall in the at bottom. So in case of the plate type wall, it show the left side show the just buckling, right? The picture show the yielding of the wall at. In case the shell has almost same failure pattern as buckling and the yielding. So to solve this problem, to formulate the strengths of the in case the yielding and the buckling, we need the important parameter. One is the material problem, material how much the strength is developed, how much the stiffness developed. So in case of the yielding, we need the strength evolution in terms of just the linear form for simplicity. So the yielding is occurred in the bottom, and the buckling is the more global the phenomena. So we need to this kind of the buckling is uh, it, its buckling shape it can be is drawn like this. But this problem also wall height is grow by time. So we have to define some interesting uh, the parameter variable wall height grow rate. L dot means L over T. So this is another expression by the Q divided by this variable. S is path uh, length, the one turn. T is a return period. Also for simplicity of we have different the expression for uh, strength evolution and the stiffness evolution by the uh, some quadratic form or the another is the linear form, exponential form. But for simplicity in this presentation, we assume the linear evolution, the assumption for strength and the stiffness. So yield strength is controlled by at the bottom of yielding by the normal stress. So strength is the normal stress. The strength is uh, composed by the square root 3 multiply the initial shear strength. So lose L means the pressure at the bottom. So we easily obtain the LP. That means the plastic collapse height LP can be expressed by the desiccation. How about the buckling strength? Buckling is a little bit complicated. So we have two approach. One is the very simple approach. We assume that just the elastic buckling of the column due to the self weight, which was derived by the green wheel. Green wheel is derived by the just the density of this the concrete controlled by low A called very similar the Euler buckling equation. So we assume that the linear strength evolution also just the neglect is the constant term to plug in this equation is very approximate buckling height of the wall and expressed by this equation by using some modification factor for kappa and psi. Psi is considered the strength evolution. K some K and kappa. This a kind of the modification factor for the boundary condition and the elastic modulus. Another important failure mode is the bond strength problem. In the very slow, in case of the slow return period, is not allowed because the bond failure between layer is very weak. So we have to assign the lower limit of the nozzle velocity. So to control the cold joint of the thin layer, we adopt the previous research the proposed this model. So the first layer already placed here, then second layer is the move from left to right. So tau is some mu multiplied the shear rate. Shear rate is nozzle divided by the thickness of the two. That is average the some velocity. So that is tau xg. Tau at sigma zg is the self weight due to the self weight. This is some average of the average of the normal stress. So we have this one. So some equilibrium state, sigma xz, sigma yz is sigma zz equal 0 is no hydro stress, hydrostatic stress equals 0. So using this relationship is plugging in Von-Mises yield criteria. So from this the relationship also with the assumption of a linear evolution of the yield strength. So return period must be the less than this one. Otherwise, cold joint is the weak cold joint expected. So using the relationship is a return period equal S over the Vn, then plug in is the previous equation into this one, then Bn is squared the less than this is complicated equation. Up to now, we have three failure modes. One is the cold joint failure. Another is the two stability strengths. One is the plastic height. One is the buckling height. So between two LP, LCL, smaller one is control the stability of the wall. So from this, the comparison of this value, then smaller one is control the stability failure. So from this equation is the wall gross velocity is derived like this. Then also the velocity of the nozzle is the equation defined by this one. So we summarize just the combined the cold joint prevention and the control of the stability. So optimal the nozzle velocity between the lower bound by the control joint prevention, and upper bound control by the stability, control by of the failure. So we have to keep between the two bound. So this is optimum velocity of the extrusion. Maybe we needed to a more complicated approach, so-called plate buckling approach. Rather than column the assumption, we get some plate buckling assumed by the wall and restrained by the elastic boundary condition. So LC bar, also LP bar, is a more complicated form. Anyway, comparison two result, a comparison by the gamma. So less than this value, gamma is already given by the some given material property. So buckling control or yielding control. So which one is control? Anyway, we can get some upper bound of the nozzle velocity controlled by the NF and Q over fail of the wall height, and so also width of the layer. So previously we already for prevention of the cold joint, this equation is already derived. So this is the for optimum nozzle velocity must be in the lower bound and the upper bound in the between two bound, and this value must be exist in this the bound two lower and upper bound. So from this is the in the line of the uh, logic, we need to define the material property by the linear form, exponential form. Anyway, also we need to the control the operation, how much the pressure, uh, depending on the viscosity, also initial strength. Yeah. So between pressure and the discharge of the concrete at the nozzle. So for construction, the wall growth rate L dot is expressed by Q over BHTL. So from this one, uh, we can assess what is minimum nozzle velocity and the maximum velocity of the nozzle, depending on the buckling or plastic failure. So, interrelationship of the initial the shear strength and the viscosity is going to the extrusion operation. Also given dimension. So what is the target of the wall height? What is control length of layer? From the given the design or construction the variable, then we have to assess the target construction time. Then from that end of total, here insert this one, okay, and of the total. So also we can assume that some wall cross the rate. So we can check what is optimum the nozzle velocity. It must be between the two bound, okay, minimum velocity and the maximum velocity. So for example, to check the validity of the research, so this is given data by the research paper. So this is QN already given by the 3D printing machine. Also some the construction some construction information is the return period of the TL. Also they require the wall cross rate LD dot here. So material property information is initial shear strength, also the viscosity and fresh concrete density, Young's modulus, and the initial the normal strength, and some evolution, the parameter of strength or stiffness, and some uh, some strength increment of some non-dimensional parameter for evolution of strength and stiffness. So alpha is this is the 5.4. Then we plug in into the some indicate what type of failure is control, gamma. So in this case, the buckling failure is control. So we have the the 1.179 meter. For in case of the approximate estimation, we apply this almost same, but in this case kappa and alpha are the psi is the 1 of 3. So this L sub CR is 0.9. So from this assessment of the failure, so we assume the V and the nozzle velocity of minimum is this one, another one is 81. So between this one we can provide some quality of what's Vn must be between this one. So Vn is almost this acceptable. Okay? Yeah. How about the shell buckling cases? Shell has a more some refined boundary conditions. So also the shape is the analytic cover. So elastic modulus also the assumed by another the initial elastic modulus multiply G star, and the non-dimensional variable is carbonication in terms of non-dimensional variable boundary condition here. The buckling length, yeah, curing rate is the psi is E, yeah. So we applied some realistic case. So this is the diameter of the shell is this value, and the thickness is 30 millimeter. So thickness is 10 millimeter. So we have the initial stress and the viscosity and the thixographic here. So elastic modulus and the curing rate of the psi E, and the initial compressive strength, curing rate, psi. So we have this flow chart for given elastic property, geometric, rheological property, print spec, select the velocity of nozzle velocity, and we need to calculate buckling length and the plastic length. So we compare which one is control, so we can decide, we determine the failure length. Then we go to compare to the cold joint. We can have some initial design, or initial the assume the initial the assumption of the velocity and the concrete discharge per second, discharge per second is acceptable. Anyway, we in this present we only focus on the stability problem, but it's we needed to more research on a large scale of 3D concrete printing to control more high quality. So we need to some topology optimization. Also, we adopt the robotics more aggressively to develop more good quality 3D print construction. So we need to how to the place of the reinforcement. So we applied the AI application, deep learning, and the machine learning to keep some steady and consistent of the quality of the layer and some material property, some temperature and the printing speed, layer height, and so on. So here is a recurrent neural network example. So maybe this is we can apply the more high-tech technology. Okay? Yeah. Thank you.
Thank you very much, Professor Hong, for your nice presentation. I think Professor Hong is logged in right now, right? So he may be able to answer the questions. If you leave your questions in the chatting box, or maybe you unmute and speak. Professor Choi, you have a question?
Professor Hong, I'm Dong-Wook Choi, Hangyeong National University, Korea. Thank you for your nice presentation. I was assuming that you were not available for Q&A today, but fortunately you are here. I just like to mention that this theoretical background of 3D printing was first laid out by researchers at TU Eindhoven in the late 2010s. And this presentation by Professor Hong, I think is a very novel approach based on some classical equations like Greenhill's and the Farn-Mises theorem, and it resulted in simplified equation that average civil engineers can use. So of course it's based on many approximation and simplification. So I just like to comment it that I thank you for your presentation and appreciate and congratulate your effort and your team and students. That's all.
Professor Hong, you have an
Okay,
additional
thank you.
comment?
Yes. So I try to simplify that process of a solution, but it has a very complicated problem. You know, fresh concrete is perfectly different from the normal hardened concrete. So we should consider the kind of the whole process. Otherwise, too much trial error to get the optimum some important variable to produce the 3D concrete. That's why so we try to develop some theoretical one, but maybe finally maybe you can more practical and simple. Maybe I already mentioned AI. AI may be one of the promising tools to develop this kind of complex process. Okay.
Thank you. We have a question in the chatting box, and actually it's privately sent to me only, so I'm gonna read that. I'm Kang Tran from Hanoi University, working as an assistant for a nonprofit project of Institute of Investment and Construction Management. The project is to develop a free e-learning hub for raising awareness of applying digital in construction. Of course, it is a nonprofit sending this message for you to ask if I can recording your webinar. Okay, this is to ask me if he can or she can record the webinar. I'm not sure about that because it's a kind of a intellectual property. So I may be able to answer that after the webinar, after several days, with the agreement of the speakers. In my opinion, because Professor Hong has developed a theoretical equation for optimal nozzle velocity, and he showed us several case studies using previous research. Maybe next step is to do a parametric studies, experimental study using variables that were used in the equation so that it could advance the state of the art of 3D printing. Do we have? Yes. In the chatting box, Dr. Tan has a question. Have you validated your theoretical models using some real experiments? I think he's doing that.
Yeah. So we just check our theoretical result with already published the paper. So right now we are doing some shell stacking problem. Is to prepare to validate our approaches. Yeah.
Thank you. Yeah, I think it's out of time. So if you have further questions, you can ask Professor Hong by email, or you leave a chatting box your questions, then he can answer that directly to you in the chatting box. Let's move on to the next speaker. Dr. Tetsuya Ishida is our next speaker. He's a professor of the Department of Civil Engineering at the University of Tokyo in Japan. He received his PhD from University of Tokyo in 1999. He served as the chair of the Technical Committee on 3D Printing Technology of JCI from 2019 to 2021. He's also serving as a chair of the subcommittee on 3D printing technology at the Japan Society of Civil Engineers from last year. His research interests include multi-scale, multi-physics of cementitious composites, and 3D printing concrete. Please help me welcoming Dr. Ishida.
Thank you. Okay, thank you very much for your kind introduction. Yes, today I'd like to talk research activities on 3D printing technology of cementitious materials in Japan. I'm Ishida from the University of Tokyo. I'm working as a full professor. And this is the contents of today's my presentation because today's title is Research Activities in Japan. Therefore, I put these items. So firstly, I'd like to introduce the activities of technical committees in JCI and JSE. And secondly, I'd like to introduce the applications of 3D printing technology developed by several Japanese companies like Shimizu, Taisei, Obayashi, Aizawa, Maeda, and Polius. These are the leading company in this field. And lastly, I'd like to briefly introduce fundamental researches on 3D printing technology conducted by our research team, University of Tokyo. And yes, today I have two items. One is live monitoring system of buildability of 3D printing technology. And also the other one is development of cementitious metamaterial with 3D printing technology. And actually this topic will be presented in the RIDEM Digital Concrete 2022 Loughborough, and this one will be held in 2 weeks, in 10 days, or something like that. Yes, so first of all, I'd like to talk the recent government initiatives in the construction sector in Japan. These initiatives has been started since 2016. And this is called as I-Construction, which try to realize the productivity revolution on construction sites. Although this data is a bit old, but from this graph, you can see the age of structure of the workforce in 2014 in Japan. And from this graph, yes, of the 3.4 million skilled workers, around 1.1 billion are likely to leave the workforce over the next 10 years due to aging. So, and the fewer young people entering the workforce. Therefore, we need to increase the productivity. And in order to do that, the use of digital technologies are promising. One is this figure shows the automation of construction machinery, which is used in Naruse Dam, large-scale dam construction site in Akita Prefecture. And also, of course, the 3D printing technology is very promising. So, yes, we really focus on this technology. But compared with other countries, the rise of 3D printing technology in Japan has been relatively slow. So we feel something like a sense of, yes, we need to catch up with other countries. Then in order to accelerate research activities in Japan, JCI established this technical committee on 3D printing technology. And this committee started from 2019, and we continued to work here for 2 years. And I chair this committee, and these members worked as a secretary general or secretary and advisor. And actually, this is the first technical committee on 3D printing technology in Japan. And yes, in this committee, the purpose of this committee is to organize the technical basis for practical application and to create new possibilities beyond the conventional framework of concrete engineering with 3D printing technology, and to provide information and motivation for next generation of concrete technology. And we, yes, this is the activities of this committee. We gather the latest technical information from Japan and abroad. And also we have discussed the application of 3D printing technology and identification of its advantages and disadvantages. And also through the workshop, we prepared a roadmap for the development of the technology, how the society changes in 10 years, in 20 years, in 30 years. And in order to satisfy the demand from the society, is what kind of technology is necessary. So we created this kind of roadmap. And also we conducted round-robin tests of 3D printed specimens. And also, yes, this is really new technology. So we discuss the unification of related terminology. So this is activities. And yes, based on the discussion, future vision or survey on the relevant technology and researches, we tried to find what is new added values and what is applicable target and what kind of necessary research exists in future. And here we have 3 working groups. Working 1, this is headed by Dr. Ishizeki, Obayashi Corporation. And we survey on the successful example in other industrial applications. Compared with the construction sector, the 3D printing technology in other fields go forward. So what kind of application was made and what kind of advantage exists? So through such survey, we can understand how to apply the 3D printing to in the construction sector. And in the working 2, which focus on the structural issue, this is headed by Professor Kunieda, Gifu University. And in this working, we discuss design, what is unique, what kind of design is possible by using 3D printing technology, and also how to evaluate, how to assess the mechanical and durability performance of the printed concrete structure. And in the working 3, this working focus on the material issue headed by Dr. Ogawa, Taiheiyo Cement. And in this working, we try to clarify the required performances in delivery phase and deposition phase for the material, and what kind of new materials and what kind of mixed proportions are necessary to realize the required performance. And also quality control and testing method is very important. So we discuss what kind of new methods are necessary in 3D printing. And this JCI committee ended in the last year. So we are moving our activity to this JSC technical subcommittee. And yes, again, I chair this committee, and these members are working as Secretary General and Secretary. And in this committee, we have 42 members, academia from 8 from the academia, and 7 people for the governmental sector, and 26 from the industrial sector. So yeah, relatively larger number of people comes from the industry. And this committee started last year, June, and we plan to work for 2 years. And we have 3 working groups: design, material print working, performance evaluation, quality assurance working, and contract standardization working. And the purpose of committee is similar to that of JCI, the survey of the latest information, 3D printing technology. And also we'd like to identify the problems in the construction of real structures using 3D printing technology. For example, technology to control the rheological properties and the strength development, tensile reinforced method, performance evaluation, continuous material supply, securing of structure stability, control at failure, etc. And after these identifications, we like to find a solution to these problems. And we'd like to discuss the applicable use cases for 3D printing technology. And our final goal is to realize civil engineering structures with 3DP, but it is very difficult to reach this stage from the beginning. So therefore, we are thinking these 3 steps toward full-scale application in civil engineering structures. The first step is a small-sized structure, that is 3D printed bench. Printing of benches along with the station building reconstruction work, and this bench deliver is scheduled in the September this year, so in 6 months. And after completing this project, we like to go to the 3D printed station building. And through this project, we conduct a virtual design of 3D printing station building. Then, yes, we'd like to go to civil engineering structures. This is the flow. And I'd like to introduce this step 1, a trial project on the 3D printed bench. This project is conducted as a part of class in the University of Tokyo in the Department of Architecture. And this is a picture which shows a discussion with the University of Tokyo students. And the students is very young and very fresh thinking. So they propose very interesting design concept. And total 14 design has been proposed by students. And in the first round of selection, three proposal has been passed. The wave-shaped bench by Issei Hirabayashi, and the bench which puts a neckline, this one, and also the name of bench is in this case new home position. And next week we will have a second competition, and one design will be selected and printed in September 2012. Of course, this is a bench, but this is a kind of structure. So through this process, we'd like to identify what kind of unexpected problem exists. Then we'd like to use this kind of knowledge to make some guideline of infrastructure. And also we visited some places where the 3D printers are located or in operation. This picture is taken in last year, the Aizawa Corporation. This Aizawa is a very leading company in 3D printing application located in the Hokkaido. And this one is last month, we visited JZC Corporation in Ishinomaki, and they also tried to fabricate this 3D printing concrete members. Yeah, COVID-19 situation has been getting better and better, so very luckily we can have this kind of event. Okay, so in this section, I'd like to introduce the 3D printing technologies developed by Aizawa, Obayashi, Maeda, Shimizu, Taisei, and Polius. Some of them very brief introduction, some of them I talk very detailed. Yes, so first of all, this is the application of Aizawa. They introduced the Saidi 3D printing machine, and they tried to make, they made a small scale reinforced concrete building. Actually, this is toilet, made use on-site 3D printed motor as a formwork. And this is an example by Obayashi Corporation, and this picture shows a shell type bench which is made with special motor for 3D printer and ultra high strength fiber reinforced concrete. Actually, this is self-compacting concrete. And the left side, this is a Shimizu Corporation example, and they fabricated a 3D printed concrete column, which is made with high performance fiber reinforced mortar outside and on-site casting, the combination of fiber reinforced mortar and conventional concrete. And this is the concrete, printed concrete by Maeda Corporation. And I think this is a smoking area. And this is a Taisei. They tried to apply the topology optimization for this kind of design. And you can see very interesting and a very unique design, which is very, which can be realized in the 3D printing and also very difficult to realize in the conventional concrete. Anyway, I'm gonna explain the detail later. And the final example is a Polius. This is a very new company, a startup company run by very young engineers. And this figure shows a warehouse building. And this modeling shape is composed of 12 building components, including, yes, this kind of round shape. And construction method is to assemble the components created by 3D printer in advance. And this is a one-story building with a width of 6 meters and a depth of approximately 3 to 4 meters and height is 3 meters. And this is a picture of the warehouse building. Okay, I'd like to add some detailed explanation on each 3D printing technology. First one is the Shimizu Corporation. And this slide is provided by Mr. Ura. Thank you very much. And yes, this is the flow. Firstly, they generate print paths on the PC. And according to this generated printed path, the fiber reinforced motor is constructed like this. And their material has very high thixotropy, so they can form 2-meter height in 2 hours. And in the next day, the concrete can be casted inside like this. And they developed their own new fiber reinforced cementitious materials for 3D printing. And they call this material as lactum, laminatable cement-based tough material. And the feature of this material is, yes, high buildability with appropriate pumpability. So as I already mentioned, with very high thixotropy, a 2-meter high formwork can be printed within 2 hours. And this material shows very good quality, uniform quality. And so this is the surface. And usually, sometimes we can see some void inside like this. Between the filament, we have some large scale void. And this is a picture of their materials, and they cut the surface of the materials. And you can see there is no visible void. So cross-section, the cross-section is very, seems to be no void, and this looks like very uniform materials. And actually, they conducted some water adsorption test. And left side is 3D printed specimen, and the right side is conventional concrete. And this test is, we call surface water adsorption test, SWAT, which was developed in the Yokohama National University by Professor Hosoda or Dr. Some other colleagues. And in the 3D printed specimens, yes, there's almost no water adsorption. That means very dense microstructure, very good concrete quality is achieved. But in the case of conventional concrete, yes, we have some amount of water adsorption. But this is usual. But in this case, very low water to cement ratio and very dense microstructure, so very high resistance against water penetration. And the feature of this material is also high ductility because this material has a fiber. So by using these special materials, they manufacture this formwork. And this formwork is transported to the construction site and assembled after next day of 3D print. And after rebar installation, the conventional concrete is cast inside. So this 3D printed formwork is an embedded formwork. So this is an example of that technology, Michi no Terasu Toyosu. And this is a pedestrian deck. And you can see very unique the shape of the column. Which is very difficult to realize in the conventional concrete. Okay, next one is a 3D printing technology developed by Taisei Corporation. And this is the introduction of their project. And yes, the background is there have been a lot of studies, particularly on material properties and printing process in additive manufacturing and construction. But few studies have conducted structural performance testing on a large scale in a systematic manner. This is their motivation. And the purpose of this study is, purpose is a practical scale verification project in terms of structural performance. Yes, so they try to make this kind of beam. Okay, so this is their printing system. Actually, sorry, I forgot to say. In the case of Shimizu Corporation, yes, this 3D printer has been developed by their own technology by themselves, sorry. So no import from the outside company, but they developed this 3D printer by themselves. And Taisei Corporation is also developed this printing system by themselves. And this is a gantry type 3D printer. And they try to use topology optimization. And this is a mixed design of their materials. The mixed proportion and types of binder or types of aggregate is really depending on the company. They use different materials. And in his case, the mixed designs like this, and they use cement, ordinary cement, and supplementary cementitious materials, and some chemicals. And the fresh properties like this, molar flow value after beating 15 times can keep about 170 millimeter for 2 hours. And this is also shows very high thixotropy, so they can build this height within short time. And as a preliminary element test, they conducted compressive strength, Young's modulus, speed tensile strength, compressive creep, and drying shrinkage with a core drilled specimen of the printed structure and normally casted concrete. And this is a comparison between the this is a comparison of the compressive strength between the casted concrete and the core drilled concrete from the 3D printed members. And the core sampling size is 100 diameter and 200 millimeter height. And so this means this diameter includes 4 filament, 4 layers. And from this result, you can see that casted concrete shows a little bit higher compressive strength compared with core drilled specimens. And also this is a splitting tensile test. And there are 2 series. This is vertical layer, and this is horizontal layer, and loading direction is like this. So from this result, yes, casted concrete shows highest tensile strength. And the second one is a vertical. No, sorry. Second one is horizontal. Yes, this direction, and the third one is a loading. So we can see this difference. And this is a compressive creep. And yes, this is a material test. And by using such a material data, okay, next they design the beam by introducing topology optimization. And here, there are 2 areas. One is changeable design area, and the other one is non-changeable design area. So no change. So for example, the upper flange, the cross-section area around the PC steel bar, and the 2 parts at both ends, these 3 parts are non-changeable. But this part can be changed according to the topology optimization. And they, yes, consider this external force and dead load and apply the PC stress. And yes, they can find the optimum design. And in this case, in this analysis, they just use elastic model. No nonlinear constitutive law is not considered. Nonlinear constitutive law is considered. Just elastic model is considered. And finally, they can create this kind of girder with 3D printing, with 3D printer. And next is a 3D printed pier. This is also very interesting. And in this case, similar to Shimizu Corporation, firstly, they manufacture this formwork with 3D printer. Then concrete is casted inside. Then finally, they get this kind of pier column. So the outer shell, illustrated as red stripes, is formed by 3D printing with short fiber reinforced mortar. And the pre-assembled rebar are placed, and then high fluidity concrete, that is self-compacting, self-consolidating concrete, are cast into the outer shell. Then is this is movie of the 3D printer and put the lever, and finally concrete is casted. And this pier, the cyclic loading test was conducted by using this pier. Yes, this reversal cyclic loading test. And yes, this is the loading and displacement relationship. Here we have two series. One is 3D printing. The outer layer is 3D printed, and the inside is self-compacting concrete, self-consolidating concrete. And the orange curve, orange line means a conventional concrete pier. And yeah, from this result, they realized that outer shell and inner concrete behaved as unity. No separate something behaves as a unity. And also from this result, the uniaxial distribution of short fiber in the outer shell enhance the reinforcement for shear force, and also we have confinement effect for the cover concrete, then which leads to very high ductility in case of 3D printing outer layer. So yeah, this kind of, by using this kind of structural dimension, we can enhance the seismic performance, and I think this is very promising technology. Okay, last one is a 3D printing technology developed by Aizawa Corporation. They introduced SAIBI 3D printer. And yes, as I already mentioned, they built this kind of toilet. And this is a structure. And this is a movie of the printing process. Like this. Yes. So yes, finally they built this toilet, and this is inside. And also they are now planning to make glamping facilities with 3D printing. And this is a picture. And as a future work, they try to introduce new machines, and also they propose very, very interesting new technology that is a combination of drone and 3D printer. And they call this is a flying 3D printer something. So if this is realized, yes, I think we can broaden the possibility of the construction process. Okay, sorry, this is the final one. This is an application example by Obayashi. And this is really new topic. The last week, they released this press news. And this is a shell-shaped bench. And this is a 3D printer demonstration building. And yes, in May this year, construction of the 3D printer demonstration building just began. And it has undergone performance evaluation review by the Building Center of Japan and has been certified by the Ministry of Land, Infrastructure, Transport, and Tourism. And 3D printer will be installed at the construction site to print the walls, and the slab is constructed, and filling it with a slimcrete. This is also a new, this is also their own developed materials, self-consolidating, self-compacting concrete, very high strength concrete. So the combination of 3D printed material and high strength self-consolidating compacting concrete. And this is a multi-layer overview of the multi-layer structure. So this is a 3D printed member, the concrete, and this is a insulation layer, and this is equipment layer. So this is also very unique. Time is limited, so just I may have one within 5 minutes, so I'd like quickly finish my talk. Yes, and this is our concrete laboratory members, and yes, we have total 30 members something, and this is a picture of a group photo. Nice, very nice. And yes, our core technology is numerical modeling, numerical simulations. I have been working with Professor Maekawa and Professor Okamura, and we have been developing this kind of numerical multi-scale modeling, multi-physics modeling. And by using this technology, we can simulate the performance of materials and structures from the very early stage to the long-term deterioration process. And in my opinion, I'd like to combine this kind of numerical model with 3D printed materials. But due to the limitation of time, I'm going to skip. And yes, this is also I'd like to, maybe I need to skip, sorry. This is also interesting, anyway. Yes, in this project, we use DIC, digital image correlation. And by using DIC, we can very nicely detect the sign of the collapse of 3D printed materials, like this. In the naked eye, cannot detect the defect, but DIC can detect. So we think we can use this kind of technology in the real-time monitoring system. And also, yes, we now develop the metamaterial with 3D printing technology. And yes, what determines structural performance of concrete? Yes, of course, depending on the material properties and the structural dimensions. And with regard to material properties, we have many possible combinations, like types of binder, types of aggregate or fiber, something. But with regard to structural dimensions, the possible shapes and sizes is limited by formwork. Therefore, yes, higher freedom of structural design would broaden the possible range of structural performance. And now we focus on this scale, mesoscale. And by changing mesoscale structure, we can create new material which has very unique physical properties. And this is an example of the anisotropic stiffness, and this is a negative Poisson's ratio. And this is a scale of material design, and this is a scale of structural design, and the metamaterial covers this range. And by using 3D printer, we can create very complex shape, then which can realize the metamaterial. This is our motivation, and this is our thinking. And by, yes, yeah, we try to make this kind of very unique structure with cementitious materials. And we apply the load. Then we can see very interesting results. Of course, pure strain hardening could not be achieved, but post-peak strain hardening was observed by making this kind of structure. So firstly, yes, we have crack like this. Then stress reduced. But after that, holes closing, then again, stress increasing. Then we observe next different crack. Then again, hole close, then stress increasing. So as a result, we can achieve very, very high absorption, high energy absorption. So this is this is a field specimen, and this is a specimen with holes. This is really preliminary study, but by changing the internal structure with 3D printer, we can create new materials, and we'd like to realize this metamaterial in future. I'm sorry, due to the time limitation, I cannot finish everything, but thank you very much for your kind attention. Thank you.
Thank you, Professor Ishida. Very nice, interesting applications and technologies in Japan. We are very glad that we have this presentation ahead of RILEM's audience. Any questions from the floor? I have a question. You showed us the seismic test of a 3D printed column with reinforced concrete core. I know that the inner surface of a printed part is rough, so that maybe interface between the core and outer crust will be good. But for the seismic application, like in Japan, in the real pedestrian bridge girders, did they consider any kind of inserts for better interface composite action?
Actually, this is a work by my colleague, Dr. Kinomura, and he joined this workshop. Maybe he would answer better than me. But anyway, yes, as you're right, due to the shape of the 3D printed structure, the bonding is really good. And after experiment, they cut the specimens and a very nice, yes, the column. So
Yes.
yeah, I think very good combination with this
Yeah.
3D printed outer layer and concrete. Yes.
I agree. Yes, we have a question in the floor. Professor Choi.
Professor Ishida, thank you very much for your excellent presentation. Again, I am Dong-wook Choi, Hanggang National University, Korea. There are many interesting aspects, but I just want to limit my question to one by Obayashi.
Yes.
You built at least a double wall by 3D printing and seems to have filled it with a slim plate, so-called.
Yes.
I think that's kind of a self-leveling one. And then you have put the extra insulation and then put some functional blocks for the environmental purpose, I assume. I thought, after looking at your slide, would it have been possible to build the two double walls by 3D printing and infill insulative concrete? Because we have a very good advance in that area also, which is almost the same as polymeric insulation. My question.
Thank you very much for your question. And first of all, I'd like to apologize because this information from Obayashi is really new. So I didn't catch the detailed design and the construction process. Therefore, I'd like to introduce Professor Choi to the Dr. Ishizeki, who provided that information to me. And probably he will answer the detail by email or some Zoom meeting, something.
Thank you.
Thank you very much.
Any other questions?
Or if Obayashi people join this workshop, please answer. No people join?
Okay, we have
sorry.
a question. Can you bring the microphone here?
Hi, Professor. I'm Hanse Moon. I'm graduate student in SNU, and I appreciate your thorough presentation about 3D printing. And I wondered, among the research about 3D printing companies, I wondered what is the technique that the company was developing. It was combination of 3D printing with drone. It seemed to fly. Can you explain about it for more details?
You mean the Aizawa? This? So
Yes,
I
drone thing.
This one? This one? Can yes. Yes, I heard from the engineer working in ISA Corporation. Now they try to combine the very big drone and 3D printer. So when, yes, now the 3D print, usually 3D printer nozzle is fixed with a robot arm or gantry. But if this nozzle is connected with the drone, the degree of freedom drastically increase. So this is their idea. But of course, it's very difficult to control how control the drone movement. And I suppose there are many research items to be solved, but now their idea is to combine very big drone and 3D printer.
Understood.
Thank you. If you
And,
have additional questions, you can leave your questions in the chatting box. And also, Professor Tetsuya Ishida will join the panel discussion at 5:30 p.m. Now, it's time for break. We have only 7 minutes. So I think it's enough time to take a break. And you come back on time exactly at 4:10 p.m. for the third presentation. Thank you. Yeah, it's already over the break. So let's move on to the next speaker. Our third speaker is Dr. Lu Trong Tan from Vietnam Institute for Building Materials. He's going to present the development of a printer and high performance concrete for 3D printing technology. Dr. Tan is the president of Vietnam Concrete Association and the president of Vietnam Institute for Building Materials. He completed his PhD regarding the UHPC at the University of Liverpool in 2008. He also developed the 3D printing concrete at Laval University from 2009 to 2011. So he's a genuine expert in this area. His research interests include high performance concrete, ultra high performance concrete, and 3D printing concrete. With that, please give him a big welcome as he's preparing the presentation. Can you share the screen, please?
Yeah, thank you very much for introduction, Professor Thomas Kang. So I will share my screen now. Okay. Okay, so good afternoon, everyone. Today, we would like to give you a presentation about what we are working with 3D printing for concrete in Vietnam Institute for Building Material in Vietnam. So in the presentation, I try to bring to you 5 contents. The first one for some very short introduction, and then I will move to the second content with design and fabrication of 3D concrete printer in Vietnam. And the third part will be high performance concrete for 3D printing. The fourth content is some products we print from our 3D printer using the high performance concrete. And also the last, we'll have some concluding remarks for discussion. A very brief introduction. So where we are from, we're from Vietnam Institute for Building Material under the management of Ministry of Construction. And the head office in Hanoi. And we also have a Sultan rank in Ho Chi Minh City. And we also have a lab site in Hà province, about 1 hour driving from Hanoi, our headquarters. So VIBM, Vietnam Institute for Building Material, founded in 1969, and we are National Science and Technology Research Institute in the field of building material, construction material, construction environment and infrastructure. And we actually assist the state management and national-wide development of building material industry, construction environment infrastructure for the Vietnam government, and so directly for the Ministry of Construction. So concrete research is one of our key research area. So basically 3D printing is an additive layer-based manufacturing technique. And you might already know some very basic steps for 3D printing. The first is 3D modeling. Objects are designed using 3D modeling software. It's very popular now. Then it needs to be format at STL format, giving information on coordination and boundaries. And then it should be slide to layers with same height, and then converted to Z code and transfer to printer for printing the material. And the material is should be high performance concrete, extruded and bonded in layer to form the object component. And now the house. All right, so 3D concrete printing, in our view, it should be the combination of the architecture functional design with high performance concrete, and we use the mechanics and automation control substance 3D printer. And actually, with myself, I joined Loughborough University over 10 years ago, and we print the first bench in the world. You can see on screen with our research team, yeah, not 10 years ago. Recent research, basically, when some very early stage of research, I joined Loughborough University, and we did a lot of tests with 3D printer. That's a 3D gantry printer. It's also very first printer in the world. And we published some very key papers, journal paper, like development in construction scale additive manufacturing process, and the mix design and fresh property for high performance printing concrete, and also hardened property for high performance printing concrete. It's I just show you the graph here, and also the citation of our journal paper. You can see over 10 years, the first paper now nearly 1,000 citations, and the mix design fresh property high performance printing concrete paper now nearly 800 citations, and the hardened property paper also have been cited over 600 times. And we found that about after 5 years of publication, 2012 and up to about, I think, 2016, 2017, it's not very, not many citations for the paper, but suddenly, yeah, near very recent years, about, let's say, 5 years, the citation number of paper increased very, very significantly. And you can see also the graph I show you here, the number of the research projects in the world come from many countries in the world, and it also went sharply from recent about 5 or 6 years. You can see on paper, because very first is the contour graphing by 2000, and Loughborough University with concrete printing about 2008, 2012, and after that we have some research center in Europe, Zurich, Delft University, USA, and China. And recently, we found very interesting about the research outcome from Japan through the presentation, the last presentation. So we can think very positively, very potential, and it should be, we feel that it very recent application for the real construction in the very short, in the coming time, hopefully. Okay. With Rust in Vietnam, Vietnam is still forbidding materials. We also work with some university like Hanoi University of Civil Engineering, and also another university, the Technology University in Hanoi called Phenica. And we try to design and fabricate a 3D concrete printer, the very first in Vietnam. And we agree with each other that some key points for designing concrete 3D printer, it should be large 3D printing system using dry system control to position the nose according to the X, Y, and Z coordinates. And using concrete 3D printing technique by extruding cement concrete material through nozzle to print concrete layers by layer. This type of design is basic design, simpler, more powerful than other options, and easy to manufacture, select locally available component, and it can reduce the cost when building a larger scale rather than robotic arm. We understand that the robotic arm, where some research center use, is very precisely, but we doubt about the scale. With the robotic arm, we very hard, inconvenient to print the larger scale construction structures. So we go with the 3D gantry printer. This is what we build, fabricate our printer in Vietnam. So we can see here, we use a printer with the X, Y, and Z, the cast coordinates. And the X-axis assembly has a stroke length 1.8 millimeter, 1.8 meter. The Y-axis 3 meter, and the Z-axis is 1.8 meter. And the printer is driven by servo motor with rotational speed control. And we can see on the screen that we design our saw, a nozzle component, including some part, assemble each other, and we use the auger system in this nozzle. And the auger driven by a servo motor as well. And with that sort of system, we did assembly, and we have the 3D printer. You can see this is a real one. This is the real one we complete last year. Yeah. And the printer, the nozzle connect with a concrete pump through a soft pipe. And we also can control the concrete pump to pump concrete, fresh concrete to the nozzle directly. And we also have a control box with our software developed. And so there are some available software in the world. And we start to design component, and we print some component. Now we move to the second part to introduce about the high performance concrete for 3D printing. We use some sort of very available normal raw material, including the cement, cement PC40, and we also have tri-PC 50. Different from other countries, like Europe, you use 52.5, but in Vietnam, 50 and 40. We use a sand with a maximum size 5 millimeters. And we also try a lot with the maximum size 2.5 millimeters. We also use silica film, we use fly ash, what is a very large volume in Vietnam market now. And chemical, we try some different admixture, but we came up with the one of the Sika admixtures. So the mix proportion optimized based on some very basic criteria: workability, the open time, strength, the extrusion, the buildability. If you have read the paper we published 10 years ago, we define what is what is buildability, extrudability, and open time. And we all know that the 3D concrete is a really challenging sort of concrete because it should be very good in a fresh property for extrusion, and but it needs to have good buildability. What we define that to build as many layers as possible in an open time. We need to keep the fresh concrete as fresh as possible. Very basic measurement is we test workability, and we need to test it after time interval to know how many minutes, how many hours it can keep the fresh property. And this series of tests, we try to optimize with different silica cream content, the fly ash content, the water by the ratio content, the water by ratio, the aggregate by the ratio. And we also vary the extrusion speed and the nozzle speed. And actually, in our test, we also use different nozzle size. But in this presentation, I just concentrate on present you about the nozzle with a 20mm diameter size. And we use a different size, as I mentioned before, 5mm in maximum size, and we also try 2.5mm. So basically, we work with the final, the optimal one. We use a 2.5mm size SAN, because actually the 5mm size SAN it get a number of difficulties in printing. The strength target was 50 megapascal. So the method of research here, we do a lot of buildability tests. And first of all, we use a motor, the small motor with the compression machine. So we use this equipment we develop ourselves, and we design and we fabricate in VIBM with the piston system, and that's a simulation system consisting of a compressor and a piston to test the buildability. And we did a lot of different mix proportion for optimization. We mix this, we measure workability, and then we put in our measurement system for buildability. This is a piston system, a small piston. The workability, we test with different mix water by ratio 0.2035 and 0.40. Sand by ratio vary at 0.67, 1 and 1.5. And we test the workability, and we measure after 60 minutes, and we found that a number of different mix decrease the workability after time. For extrudability, we try to optimize by variation of speed of the nozzle, 40 millimeters per second, with extrusion speed 40, 60, 80, 100, 120, 140, 160, 180 millimeters per minute, with 20 millimeters per minute interval. The nozzle diameter we test using 20 millimeter diameter, and you can see here the extrudability. Some mix not really good, and finally we find some mix has had good extrudability. And the extrusion speed should be 100 to 140 millimeters per minute. The buildability with different mixes, we have a different performance of buildability. And you can see on the screen different sand binder ratio, different buildability performance. And it seems that with the water bioratio, higher water bioratio, a bit better buildability. But it also, we understand it depends on also other factors. So the higher water cement sand bioratio, the better buildability. The higher water bioratio, the worse buildability. Just in general. Yeah, you can see a very short clip to show we test our ability with only one single layer. One single bit, and it can build with different layers, using different mixes. So the buildability actually with water bioratio 0.35 mix also have good buildability, but it's not really smooth surface of filament. With 0.4T, quite good buildability, and smooth surface for smooth surface of filament. So we select water bioratio 0.4 for test in the real printers. And also, as I mentioned, we vary the ratio of the sand and binder, and we also found that they also have a quite good buildability, but lower sand binder ratio have a good binding between filament and smooth surface of filament. So we use actually the big printer for printing a number of blocks like that for test different direction of the concrete printing. Here is one of the block we print using our printer. And after being printed, the block was cut to make a number of cubes and beams for compressive strength test and flexural strength test. And we also print a number of blocks, and we cut it to make some sample for bond test. So we try to apply the tensile load to determine the bond strength between layers. We also print and measure a number of specimens for drying shrinkage. So we can see on the screen the cube, the beam, and also the tensile, the bond strength test with the specimen shown in the lower right corner pictures. Right, so the reason with compressive strength, we also compare with cast specimen. You can see here with a different graph: 3 days compressive strength, 7 days compressive strength, and 28 day compressive strength. And the printing direction really influence on the compressive strength. And we found that the compressive strength in x-axis specimen is the lowest one, and the y-axis and the seem better compressive strength, and the z-axis also quite is higher than the x-axis specimen, but At 28th day, finally, it's lower than the y-axis. So the comment here is a compressor strength of printing concrete. We found just about, it's vary from 30 to 60% that of casting specimen. And the compressive strength is X direction is lower than that in Y direction. Quite similar, quite similar ratio of test result with flexural strength. This is without fiber, and we also measure the flexural strength of 3 days, 7 days, 28 days. And we compare the printed specimen and the cast specimen, and we found that flexural strength of 3D printing concrete without fiber is equal to 30 to 40% that of cast specimen. And also the flexural strength in the X direction is the lowest reason. With the fiber, we add the polypropylene, micropolypropylene fiber, and we found that it improved the flexural strength in 3 days, 7 days, and also 28 days. And the flexural strength of the fibers printed specimen improved to, and it's equal about 50 to 70% that of cast specimen. And we also measure drying shrinkage and compare the printed specimen and cast specimen. And we found that it actually quite similar result up to 28 days. And when we add fiber, 0.5% and 0.7%, the drying shrinkage improve. Yeah, that means the value is lower than the non-fiber specimen. So we have a printer. We also have the high-performance concrete. Then we did a number of printing with different products. The first one we tried with the curvy chair, and we were successful with printing this curvy chair. It's just one single bit. So actually, it's not strong, really strong. Yeah, so that's just model to show how our printer can work for the curvy object like a curvy chair here. And the size is the height is 1 meter, and the width, the wide of the chair is 0.65 meters. And we move to another more complicated shape objects that we print. We try to print a curvy chairs and table with a size of 1.9 by 0.7 by 1 meter. And this you can see here, we did 3D modeling. Then we slide the object to our website software, and then exported as a Z-code file for printer. And so we complete the printing of this curvy chairs and table, and it it's strong enough, yeah, and carry 2 persons at the same time. And it now in IBM. Hopefully one day, yeah, some of you visit us, and you can visit on site, yeah, in our institute. Okay. And after that, we try to build a bigger one. This is a sentry box, 2.6 meters high, and 1.8 by 1.8 the plan. Yeah. And we had a lot of discussion about how to print it, yeah, with our printer. Actually, we can print one shot for the whole sentry box, but it's really hard to move it out of the printer. So finally, we made decisions that we will print 3 different components, and we would assemble them each other. So this is the first component we print. Yeah, show you on the screen. It actually quite curvy behind in the half of the sentry box cross section, and the wall you can see here a lot of void. Yeah, and we print the 2 sides of wall, and we print the zigzag filament inside of the wall. Anyway, I will show you later on a short movie about how to print, how to design and fabricate a printer, and also how to print some components. You have more understanding about what we have done. Okay. So this is some pictures show you component we print. Yeah, this picture to show you how we move 3 different components outside of the laboratory, and we did assemble 3 components. And the high performance concrete, so that strong enough. Even the component you can see here, it could be moved and rotate outside of the lab, yeah, with a very simple cable and crane, yeah, the crane motor, and we were successful in assembly 3 components with each other. Here you can see the complete sentry box. Yeah, that's what we did in VIBM. Anyway, okay, I will show you a short movie about what we have done, and maybe you have more understanding about what we have shown here. It's a Z-axis we design. It's an X-axis with the nozzle mount on the X-axis. It is a yes, it's a nozzle design. It's a nozzle mount on the X-axis. This is a control board we design. Frame fabricated in workshop. This test durability system testing. It assembly. print the curvy chair in one socket. See the concrete print smoothly. Just a fiber concrete mix. Okay, so that's I think the content we show you, and now come to the concluding remark. Yeah, in our research, a 3D concrete user XYZ decaf GAN 3 printer has been designed and fabricated successfully with overall dimension 4.9 by 2.5 meters that can print objects with dimension up to 1.8 by 2.5 meter. High performance concrete having good texturability, buildability, open time, and over 50 megapascal compressor strength, and also over 8 megapascal compressor strength. And less than 0.2% drying shrinkage have been developed, and it can be usable effectively for 3D printing. And the material and the printer has been deployed to print successfully some architecture object, set of curvy table and chair, and a center box. Okay, that's it. Honor I bring to you in the second ACF webinar.
Yes, thank you, Dr. Ta. Actually, your microphone voice is very lowered after the video clip, so you may want to raise the voice.
Sorry. Yeah, now you hear me clearly? Yeah.
Actually, it's very low.
Can you hear me now?
Yes, it's better.
Okay.
My quick question is, your high performance concrete with steel fibers?
No, I'm sorry, no, not steel fiber. That's a soft fiber, plastic PP fiber.
Short plastic fibers, okay.
Yeah, the polypropylene microfiber.
Okay, polypropylene. Okay, so no problem for nozzle congestion or anything.
We have some problem with congestion at the nozzle when we try to increase the volume of the fiber. So if over 0.5%, it should be got clocking stuck at the nozzle.
Right. So I mean, I think that's the future direction for the 3D printing technology, using some kind of a fibers. The other way is to spring the fibers together with the, 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 the fresh concrete extrusion. Questions from the audience will be welcome. Can you show me the chatting box? Okay. Flying robotics can be applied in the future in hazards or disaster areas. That was a comment. Thank you for that. I think the power of the 3D printing is to create the very complicated shape of the structure. Like you showed us the very old temple of Vietnam. Right now, 3D printing, texture is all like additive shapes with that more like a donut doll. But in the future, it could get similar to the small scale 3D printing using plastic materials. I mean, that texture is good enough for us.
Yeah, I think that's quite historical one. And some of you, if you visit Vietnam, maybe you also visit that's actually the first university of Vietnam.
Oh, okay. So if we have no further questions, let's move on to the final speaker, Professor J. Sanjayan from the Swinburne University of Technology in Australia. His top title of the speech is the Research Advances in 3D Concrete Printing Technologies. Professor Sanjayan is a structural engineer specializing in concrete materials technology with more than 30 years of experience in teaching, research, consulting. And he is the director of a Center for Sustainable Infrastructure Digital Construction at Swinburne University of Technology and led the development of a digital construction lab. His project include 3D printing, low carbon concrete, geopolymer concretes, and the use of phase change materials in construction. With that, we'd like to give a warm welcome to Professor Sanjaya. Could you share the screen, please? Yes, thank you very much.
Can you see the screen?
Yes, very well.
Okay, thank you. So thank you, Mr. Chairman and ladies and gentlemen. Thanks for inviting me to present at this webinar. So I'll be presenting some of the work that we have done in recent years in 3D concrete printing. So I like to show this slide just to the reason why we need to do automation in construction. So this is some of you may have seen this graph. The productivity in the construction sector in the last 20 odd years were compared with all the other industries and also compared with manufacturing industries. The manufacturing industries have doubled their productivity, but the construction sector has remained reasonably stagnant in the last 20 years. So the reason why this productivity is stagnant is because the manufacturing sector and the automotive, aerospace, and shipbuilding, they use CAD modeling, additive manufacturing, and automatic assembly methods. Whereas in construction site, we have low labor efficiency. If you go to many of the construction sites, you see a lot of people just standing around, waiting for something and waiting for this. We have very high accident rates in construction site, and also have very difficult quality control. So this translate into the cost, because where the benefit of high productivity efficiency is that we can have lower costs. If you compare the construction costs in the last 50 years, it hasn't changed. It has actually gone up ahead of the wages compared to if you think about manufactured good, they have significantly come down in price compared to the earning capacity of people. So it is important that we look at automation in construction, and 3D concrete printing is only one aspect of the automation in construction. So this is the that's the reason we started this digital construction lab at Swinburne University of Technology. We are in Melbourne, in Australia. So we started with the robot printing, 3D printing. This is in 2016. We started with small scale, but now we have grown to a big group of people, and we also have a large 6-axis 3D printer. So we can print about 8 meters long, 6 meters wide, and 4 meters high. So we haven't printed anything that big, but we just got the capability. But most of the work that we are doing is research, so it requires small size printing. So the main advantage, as others discussed, is there's no formwork waste. Formwork constitute about 60% of the cost of concrete construction, and also constitute a significant waste. We still use a lot of manual methods to 3D print. So this is our mixer. We mix it, and then it's printed on this side. So we pump the materials near the 3D printer, and then we mix it again and then print it. We organized the first international conference. We initiated that in 2018. At that one, most of the people in the world working in 3D concrete printing were there. And then the second international conference was held in Tianjin. That was in 2019. And then the COVID came, and we did not have the conference for 2 years. But the third international conference in this series is actually starting tomorrow. So in Shanghai. So it's tomorrow and day after tomorrow. We have a very active program in Shanghai on this topic. There's a lot of activities going in China. We have a collaboration with Hebei Institute of Technology. So for the second international conference, we printed this bridge at the university campus. That's a 20-meter span. So the opening was during the conference. This was the opening ceremony. And this bridge was a replica of a famous bridge in China that was built around the 10th century, I think. Yeah, it was about 1,000 years old. So the way that we built was we built them in a lab about a kilometer, about 2 kilometers away from the site, and then brought to the site and constructed. And these are the students printing the components of the bridge. These are students who never built a bridge in their whole life. So it was a very interesting experience, interesting and learning experience for everyone. And in the process, there were so many issues. They ended up building the bridge a few times, about 2 times to get that finally right. So, so one of the main issues in 3D concrete printing is the buildability. So some of the earlier speakers also mentioned this. So when you print with soft material like concrete, we can have this kind of situation. So the main issue to improve this is the yield stress, because the yield stress of the material, if it's sufficiently large, then we can build much higher. And also the yield stress, this is a Bingham model where it changes with shear rate as well, but that is not that important. That is only important for pumping. So if we increase the yield stress a lot, then it's difficult to pump. So it is the compromise we have to do. So the rheology of concrete is an important way of improving the yield stress, but there's a limit. We cannot increase the yield stress beyond a certain limit, then we cannot pump the concrete. The other option is to have a fast setting concrete. So the moment it comes out, it sets, so the yield stress can improve very quickly. So let's look at the demand. So we need a concrete that has good pumpability. That means it should have high workability, low yield stress, and low segregation. But it should have long open time, otherwise it will set in the pump. So open time is the time from the mixing to how long before it's set. And the other is extrudability. So for the concrete to be extrudable, it should have some medium level of workability. If it's too flowing, then the concrete will come out as a fluid, it doesn't get extruded. So it should have some yield stress, medium yield stress. But then to get buildability, we need high yield stress and fast setting. So we actually have contradicting demands. Here we want low yield stress, here we want high yield stress. How we can achieve different requirements from the same concrete? So there is a contradicting rheology and setting time demands, and we can, and also if we stop the 3D printing at any point in time, if you want to take a lunch break, we need to clean everything before we can go for, we can stop even for a few hours. So the best, one of the solution we think is an active rheology control. That means we control the rheology at different positions using different technology. So one of the things that we are investigating is a short duration near nozzle mixing. So the nozzle is the print head where the concrete's coming out, but we mix the concrete near the nozzle, so there is not a lot of pumping distance, and we bring the water and liquid additives and dry materials and mix it here and print it. So in this technology, we don't have a lot of mixing time because the mixer is very small. We can't carry a large mixer. So we only have about 50 to 30 seconds of mixing before it's get extruded. So that is, and the hardening time should be between 1 to 2 minutes. So we can have a mixer that is very close, so it doesn't take a long time to transport from here to there within seconds. So normal concreting, so with this technology, if we need to stop the concreting, we only need to clean this part and take a break or come back tomorrow and start again, because all these dry materials and wet materials come to this, they don't need to be cleaned. So this is the main advantage of this technology that we are currently working on. But normally we mix concrete about 5 to 10 minutes in a big efficient mixer. How we can change that to 15 seconds? That means we need to understand what are the parameters to improve the mixing efficiency. The mixing is a field of concrete that has not been studied in the past. So we have to go back to fundamentals and start to understand what are the parameters that we need to improve so that mixing can be quick and at the same time have high quality mix at the end, because we don't want to compromise the mix quality because we did not mix long enough, or we only mix for 15 seconds. So these are some of the work we did, and the first group was the strength of concrete after mixing for 15 seconds, and then and cast and the 7-day strength. This is 30 seconds after 7 days and 90 seconds, and this is control. The control was mixed for about 10 minutes. So you can see that we could achieve for this particular type of mixes, the strength after 15-second mixing is just as good or even better than the control mix, which is using the traditional concrete mix. And these are concretes that have strength between 40 to 50 megapascal. So how, so the 58 is 0.58 is the water cement ratio. So And these are different coarse sand, fine sand, medium sand, and so on. So we made a lot of mixed designs, and what we found was the packing density and sand size. That is the key. So when you have low packing density, so that means we pack the solids without the water, and then we add the same amount of mixing water, and we add the water. The excess water that's remaining is a lot more for concrete that has, or the solids contents that has high packing density. That means you have more water for mixing, so you get a better efficiency. So this is what we found. We could improve or reduce the mix time without compromising the quality of the concrete by having a high packing density. And this is some microscopic images, and you can say this is 15-second short duration mixing. The first 63 shows 0.63 water cement ratio. Sorry, the binder to sand ratio is 0.63. This is 0.53. And you can see with the 15 seconds, there's some silica fume is still not dispersed, but when you go to this particular mix where the binder to sand ratio is 0.53, that the 0.53 gives a better packing, a high packing density. So with the same 15-second mixing, you can have a better dispersion just by having high packing density. We also measured the power consumption. So the power consumption is lower for concrete mixes that has more high packing density. And then we did some 3D concrete printing trials. And this is, we mixed at the nozzle for 15 seconds. This is at 30 seconds. This is at 90 seconds. In terms of mix quality, we got much better quality at 30 seconds. Because when we mix for 90 seconds, the concrete start to set, the yield stress is too much, and it's get cracking, it's harder to extrude. And when it's 15 seconds, it's not sufficient mixing. The quality is also not good. The other method that we tried for active rheology control is we place a very stiff concrete using some conveyor or belt or some other methods, not pumping, because we cannot pump the concrete. And then we use a vibration. And the vibration makes the concrete yield stress, it reduces the yield stress and make it become extrudable concrete. And that can only happen to concrete that is thixotropic. Thixotropy is a property or rheological property that means that concrete, when the concrete or the material is vibrated, it starts to flow. And when you stop vibrating, it becomes stiff. So because we are vibrating, the concrete starts to flow and we can extrude it. Then as soon as it's extruded, it's not vibrated, and it's not going to regain its stiffness. So we did this test with the RAM extruder. So we had a vibrator attached at the end, and then we were extruding. And what we found was when we have no nanoclay, the vibration made no difference to the yield stress. But when we have about 0.3% nanoclay, when there's no vibration, the yield stress is very high. It's about 35 kilopascal. It's very stiff, very, very high yield stress. And then as you increase the vibration, the yield stress start to drop. So the effect of vibration is significant when you add nanoclay. What does nanoclay do? Nanoclay makes the concrete thixotropic. It increases the surface area of the particles, and almost everyone doing 3D printing now adding nanoclay, but they are not using vibration. But 0.1% nanoclay or 0% nanoclay, they're not sufficient to introduce the thixotropic properties. So is the nanoclay and the vibration is enough to create that thixotropic properties, and then we can control the rheology. So so this is M0, no nanoclay. We can only build up to about 100 millimeter height and then start to collapse. We put 0.1% nanoclay without vibration, and then with vibration we can print with almost similar height, but it's difficult because it doesn't the vibration doesn't make big difference to the flow. But when we put 0.3% nanoclay, the concrete becomes thixotropic, and the concrete start to flow nicely. We can print it, and we printed up to 1.6 meter high, and then we could keep going, but that particular printer that we were using, that was the maximum height. So it could have printed more. So this shows the effect of active rheology control. So here, this is the 0% nanoclay, unvibrated, vibrated, no big difference. 0.1%, there's some difference. This is we cut the concrete and looking at the photographs. So when you unvibrate a thixotropic concrete, you are not going to have good adhesion between the layers. The vibration is essential for the concrete to start to flow, and it will get good bonding, but at the same time we can have high stiffness concrete. So that is active rheology control. The other technique we are using is mixing at the nozzle using geopolymer concrete. And geopolymer concrete, by adjusting the activator, I hope most of you are familiar with what geopolymer concrete is. It doesn't use any cement, it uses only fly ash and slag, and we can put very high levels of activator, mix at the nozzle, and it can go hard very quickly. And by using that, we can almost print horizontal with very little sag. So I'll show you, yeah. So show you again. This is printing with geopolymer concrete mixed at the nozzle. And we also did a lot of discrete element model calculations. We looked at different type of modeling, but at the end, the discrete element modeling is the best for modeling rheology of concrete. We have, I think, because I only got 10 more minutes, so I might just move on. Now, the other issue is reinforcement. Reinforcement in 3D printing is hard. A lot of people are using fibers like us. But we come up with an in-process mesh reinforcement method. So we put the reinforcement as we print. It is using a nozzle in-process mesh reinforcement. So the mesh reinforcement comes through the nozzle. The nozzle is split at the end. So this is some pictures, and we print with overlapping nozzle, so overlapping mesh. So this shows how this is done. So the mesh is printed, and then we print the second layer. So the next, so we published a few papers on this. So this technique, when you finish printing, it is same as continuous mesh. The other technology that we have also done a lot of work is powder bed 3D printing. So the powder bed is, we lay cement, sand, or in this case, we also printed with geopolymer. We print the powder, we lay the powder by layer by layer, and then the ink, we print like we would normally print in an inkjet printer, but the ink is water. So we print the water and ink layer by layer. The layers are only about a millimeter thick. So we can print very intricate shapes without, and the overhangs and other things are not a big problem. We can print any shape. But the main issue is we end up with a lot of dry powder that we need to recycle. And this is what we end up printing. This is, it would be very difficult to print with the extrusion method. And with this method, the main issues are the binder droplets, and we have to model how far they penetrate. If they penetrate too far to the previous layer, it's not good. If they don't penetrate enough, it's not good. They should be just sufficient to only penetrate that part. So we did some work with high-speed camera to characterize the droplets and how quickly, how many microseconds it takes for them to penetrate into the powder bed. And based on that, we can optimize the powder particles, which is important because that needs to be matched to the water or the ink. We call it ink. And with this technology, you can print something, quite large structures like that. But this particular one was printed with sand and resin, not cement. But we can use the same technology to do that. And then we also wanted to do it with larger aggregates. So we use large aggregates, and the feeder was paste, which is cement and water. So the cement and water get mixed, and then allayed. So the ink is your paste, and the aggregates is the bed. So so you can see this. We are extruding the paste binder, and then we like that, and we do layer by layer, and then we finish printing, and then this is what we printed using this one. It's early stages, but this had an aggregate content of 40%. So the problem with this is the aggregate size is going to decide the resolution. We also are printing with ultra high strength concrete, which has a very high flexural strength, about 37 to 40 megapascal. The compressive strength is about 120 to 144. We were aiming for 150 megapascal, which is very common if you cast the concrete, but we were doing it with 3D printing. But it is a way to print without having to put reinforcements, because we have very high flexural strength. This is something we did to print with transparent columns. So this is, you can see that we put optical fibers when we were printing in between the layers, and then we could have concrete that is transparent. This is one of our students' idea. So there are things that we can do that. So in conclusions, the digital transformation of construction offers many opportunities, but we also have a lot of challenges. Reinforcements, to build overhang. How do we build overhang? So we looked at the idea how people printing with polymers and so on, and they can print overhang because when the polymers melt, and when it comes out of the nozzle, it goes hard immediately. But concrete doesn't go hard immediately. So this is something that we are working on right now. And also in the future, we need to look at durability, design standards, and so on. But it's a little bit too early because we are still working out the technology. But you know, 3D concrete printing is suitable for mass customization. And these are some of the, so we have published a few papers. If you search under my name, Sanjayan, you will find some of the work that I have presented today is been published in these papers. But what we really want to print is interesting shapes. There's no point copying rectangular shapes. So these are some of the shapes printed by people around the world. This is in Netherlands, bridge. This is another bridge. Most of you have seen it, I think in Venice. This one is very interesting shapes. So yeah, that's my presentation. How do I stop sharing? Hello?
All right. Thank you very much for your presentation. Very nice. A lot of technologies and applications, and we learned a lot about the 3D printing. Is there any specific question to the final presentation? Yes, Professor Choi.
Professor Sanjayan,
Yes.
this is Do-Guk Choi again from Korea. I thank you very much for your excellent presentation. It's full of new and innovative ideas, in my opinion. There are many interesting aspects. I have 3 short questions now. First one, you mentioned of very rapid hardening, such as 1 to 2 minutes even.
Yes.
From my experience, even though you use special cement, such as sulfur aluminate cement, probably the initial set begins after several minutes, maybe in the order of 10 minutes, something like that. In fact, I never used it without any retarder, but that's my first question. Maybe you have used the geopolymer. My second question is about your rapid mixing. For example, 30 sec mixing is very short time, especially with highly well-packed powders. So but I must assume that you have used several different rotation speed during that short time of 30 sec. My third short question is about use of nanoclay. I fully believe that this 0.3% nanoclay will provide some shear thickening behavior, which is, of course, needed. But in this case, I think you utilize nanoclay rather than for the shear thickening, but for the large surface area for the purpose of fast set. Am I correct? I have 3 short questions.
Yeah. So I'll start with the last question. Thank you for the questions. The nanoclay is used for shear thickenings. You're right. But I said the large surface area because the shear thickening characteristic is because of the large surface area of the nanoclay. That's what I mentioned, large, but the nanoclay provides the shear thickening behavior, which is the thixotropy behavior. Your second question was, can you remind me? It was about the
during mixing.
Yeah, the mixing speed. We use mixing speed between 60 RPM to 300 RPM. When we increase the mixing speed too much, we end up with a lot of air in the mix. So there is a balance of, there's an optimum speed where we get a good mix without putting too much air. But I think the particle distribution we find is the key, because the mixing speed or the power is limited, because we want to put the mixer at the print head, and the print head cannot carry a very large motor because the print motor is very heavy. So we want to put a small motor. That means we are limited by how much rotation or mixing energy we can put in the mix. So, so we are limited by the mixing energy. So there are some boundaries. And also the first question you asked for the quick setting. Yeah, the one that I showed you was geopolymer. Geopolymer is very easy to adjust the setting time because we can adjust the activator dosages. Whereas, but we have also done same work with normal concrete using accelerators. We have used some shotcrete accelerators that go hard extremely quick. We have damaged some print heads because they go hard inside the print heads sometimes. So they are extremely quick. The problem with when it goes too quick is the interlayer bond is not as good, because when you are depositing the concrete, it should have sufficient wetness or workability to bond to the previous layer. If it's set too quickly, then it doesn't bond. If it's too slow, then it doesn't have enough strength. So these are the parameters that we have to work with. Yeah, thank you for the questions.
Okay, thank you. If we have no more questions, let's get started the panel discussion in 2 minutes. Okay, so that all the speakers hopefully join the panel discussion in 2 minutes. Okay, because we are behind the schedule, so we have about 20 minutes till the end of this second webinar event. But we have already a good discussion shared between the audience and the speakers, so maybe 20 minutes will be good enough. My name is Thomas Kang at Seoul National University. As, as I introduce myself, I'm the moderator of the first and second ACF webinar, and I'm the chair of the educational board of ACF. And I'm very happy to have 4 excellent speakers with timely, important topics, and still very developing area of a 3D printing and construction automation. I already learned a lot about the technology, but I hope I can learn more during this panel discussion. And I would like to introduce Professor Dong-Uk Choi at Hanyang National University in Korea. He's the president of ACF. Do you have any?
Yes, Thomas, thank you for kind introduction, and I really appreciate these 4 presentations that we had. We had a privilege of having these 4 presentations. For the purpose of this panel discussion, I'd like to begin with some topic that is very popular these days, that is sustainability. Of course, we have many agendas for this 3D printing, to my knowledge, but nowadays sustainability should also be a topic that can be considered in almost all areas. During today's discussion, at least two speakers mentioned about their sand, sand binder ratio of 0.67 or binder to sand ratio of like 1.5. This is a lot of binder and it leaves a lot of environmental footprint. 3D printing also use sand exclusively, and there are some attempts using a larger particle size these days. But in fact, good sand is also becoming a very rare commodity nowadays. It's not everywhere anymore, it seems. So maybe we can approach from material side about how we are going to bring down some environmental footprint, and probably we can discuss in two aspects, binder and sand.
Yes, I mean, there's a strong movement for the ESG and sustainability. So low carbon footprint is another important aspect. Does any speaker have this um, solution or potential suggestion?
Maybe I can say something.
Yes.
Chen? Yeah. So like our Japanese Professor Ishida showed some slides where they printed the formwork, and then put the reinforcement and cast the concrete. That is that type of technology is using only a small amount of concrete, which is the outer layer, is 3D printed. So in terms of the material consumption, it is only a small part, and we are using sand. We are not using high coarse aggregates, but we are also using high cement content, which gives a very high quality cover. It gives a long-term durability for the concrete. In addition, we are not using formwork. Most of the time we use timber formwork. They are, after the formwork concrete finished, we throw away the timber, which is a significant amount of waste. So, so if you look at it from that point of view, it is more sustainable than conventional construction. Also, if you want to make a column which is long-term durable, you increase the or reduce the water cement ratio for the entire column, whereas you only need to reduce the water cement ratio for the cover. So we are actually making a concrete structure where we only put durable part where it's needed. So in many ways, so the inside concrete can be a low binder, high water cement ratio concrete. So in many ways, this can be more sustainable.
Thank you for your comment. I have also a suggestion. Because 3D printing is very strong in shaping whatever we want, so that we can apply the topology to come up with the you know 3D printing shape with only compression parts of the members. That way we can reduce the weight and then volume of the concrete. So the greatest benefit of a 3D printing is to create any kind of a shapes. And it's actually in line with the reduction of the volume. We don't need unnecessary parts of the structures. So I want to emphasize that advantage of the 3D printing. Any other comments from the other speakers or audience? Because I mentioned about the compression resistance, because there's a drawback of having the tension reinforcement in this type of a production process, although slit nozzle was shown or some other ways of providing tensile reinforcement was shown in this webinar, it's better to apply this 3D printing technology to more like a compression resistant members or shapes. So, for example, like a containment structure with pre-stressing, we can have only the compression parts of the concrete, for entire surface. And arch shape is also another example. So, I mean, how we can overcome that the difficulty of having reinforcement in tension.
Well, Thomas, I have one idea also that I can think of is using some coarse aggregate to a certain degree. Nowadays, I see some papers that have used like 8 millimeter or even 10 millimeter coarse aggregate. Of course, this will provide some volume stability, like low shrinkage. It less energy intensive to produce. It can provide good aggregate skeleton, and probably will reduce some amount of binder. So, well, that may be an option, in my opinion.
Yes. I mean, the Dr. Tan and Dr. Ishida showed us application of short fibers, polypropylene fibers. I mean, I always wonder, how can we make 3D printed structures equivalent to conventional reinforced concrete? I mean, reinforced concrete, we can have steel reinforcement anywhere we want. So I know there's a future of a 3D printing concrete, but we want to make it comparable to normal reinforced concrete.
While we are talking about reinforcement and fibers, I think we can move on to the second theme, perhaps,
Yes.
which is reinforcement. Of course, TU Eindhoven, I think, introduced about 4 years ago the wire printing at the same time in the same direction of this extrusion. And I think about the same time in the Nanyang Technical University, Singapore, also introduced a similar technology using stainless steel wire strand, also printed at the same time with mortar in the same direction of mortar extrusion. And today, Professor Sanjayan introduced a very special technology of this using steel mesh, which is going in the outer plane direction, interlayer, which should be very efficient also. I think I remember similar technology from China, perhaps Hebei University, where they have used the U-pin, about 20 millimeter long and 1 millimeter diameter, which is also installed across the layer. So this is interlayer reinforcement in a similar sense to Professor Sanjayan's research. So maybe we can talk a little about this, how we are going to reinforce this 3D printed mortar.
Yeah, there's another question from the audience in the chatting box. Did anyone try to use steel fibers to reinforce the 3D printed concrete? It could be a problem with extrudability with this kind of material. I also heard about the congestion problem in the nozzle, so that the other way is to spring the steel fibers separately near the nozzle, so that the fresh concrete and steel fibers are both like a shooting at the same location. But I am not the expert on this technology, so any the experts and speakers can answer this question.
Y- Yeah, maybe I can make a comment. We've done a lot of printing with steel fibers, especially the one with ultra high performance concrete that requires a lot of steel fibers. So it is just a matter of getting the mix design right. So of course, when you start, it will start clogging, but then you adjust the mix, you can get it right.
So there are ways. It's
Yeah, we
just
can look at some of the published works that we have. You can look at it and say we optimize the shape, size of the fibers, aspect ratio of the fibers, the mix, and eventually you will find something that works.
mhm. Professor Ishida, Professor Tan, do you have some other opinions?
Yes, I think, yes, it would be difficult to use steel fibers. I'm not sure. In Japan, many people use PVA, aramid fiber, basalt fiber, yes, more flexible fiber in 3D printing. So,
Mm-hmm. Yes.
Yeah, in my view, yeah, we also have not tried the steel fiber yet. I remember some in literature reviews, some other groups, they also test with fiber, steel fiber. It's not really popular. We also use the PP fiber actually to reduce the shrinkage rather than improve the strength. I have another comment, and maybe if we would like to discuss about, we know just a 3D concrete printing, we can print some very complicated architectural component. The thing is, now different group, we try to print some structure in-house, and another group try to print the structure and even a house outdoor. So, like in the presentation from Professor Isida, you also show some structure like a formwork printed in-house. Then you try to move out of the lab, did transportation to the on-site, and you did assembly them each other. Yeah. So how about your views and other expert views about 3D printing should work with in-house structures or outdoor structures? How about your views about that?
Yes, can I talk a little bit? Yes, in future, I think it would be nice to have a 3D print outside. But in the case of outside, temperature, humidity varies a lot. Therefore, sometimes material extrusion becomes very difficult. The concrete becomes stiff, something like that. Therefore, in future, we need to develop very stable materials resistant to change in temperature and humidity. And that is also very important research items, I think. But before, as a first step, I think the 3D printing in-house is very easy and we can control. Therefore, yes, gradually, yes, from in-house to outside. I think this is the progress of application of 3D printing.
Yeah, we also did quite similar thing. In my presentation, I saw we print 3 components in-house, and we move out and we assembly them each other. But because I saw in your presentation, the formwork is quite thin.
Yes.
Quite thin. So what's the strength of concrete you have used for the formwork?
Yes, that depends on the company or depends on technology. But the water to binder ratio is around from 25% to 35 or 37%. So in some cases, the compressed strength reach like 80 megapascal something. In some cases, 30 or 40 megapascal. So very high strength and a very dense microstructure. Yes.
Yeah, we also use over 50 MPa. And because some experts in Vietnam, they claim that if we use a 3D printing, we just print wall only, so we don't need high strength concrete. However, because we understand that the 3D printing is a layer by layer structures.
Yes.
And the bond between layers, that's the key point. We need to keep, we need to have a good bonding, and high strength concrete help support that that point. So that's why we still use high strength one. We did a comparison about the cost, compare the worn 3D concrete printing with other methods of build the wall. And it's quite interesting that even we have the higher price of materials, but the total cost is lower than other conventional wall building.
Yeah, that's due to removable formwork and less labor. While we are speaking with Dr. Tan, I have one short question. You use sand binder ratio 0.67 and 1.0 and 1.5. And out from buildability and surface quality, you have chosen 0.67.
0.67, yeah.
Yeah, right, which is a good amount of binder. And I was hearing that, and I wondered why we should care much about the surface quality, because 3D printing in one hand is a good shows good texture, very unique outside, and inside we can shotcrete always. And I think maybe it's better in case of fire or something, because this extruded 3D printed surface has a lot of surface area and more chance for water escape at elevated temperature. So in my opinion, inside shotcrete is better. Outside exposed is good. What do you think?
Yeah, I think as an expert, especially the architect, they also comment about that. They prefer the rough texture of 3D printing. That's a good point. And yeah, come back with your comment about the ratio between by the over the sun. Yeah, we we saw that we did a number of tests with different ratio 0.67, 1.5, and yeah, the thing is not we the ratio 1 and 1.5, it like it the struct the yeah the specimen, we found that it got some sort of crack. It quite hard to print that, so we have to use a higher binder content. However, we try to replace cement with fly ash. We did vary 10, 20, 30, 40%, and we use the 20%. And the thing is, because our research, we try to make sure that the structure we printed should be strong enough for moving, transportation, for assembly. The thing is, with 3D printing now, one of the challenging points is to predict the failure load, the load capacity of the 3D printing components. So we find difficulty in prediction of failure load. So for the safe side, we use high strength concrete for that, and we plan to also plan to do some sort of research about the prediction of the load capacity for 3D printed component. That's quite challenging, actually.
I have one question to Professor Ishida. I hope he's still with us.
Yes.
Yeah, right. Yeah, you introduced the JSE committee on 3D printing,
Yes.
and your split tensile strength test, for example, was very interesting. So I'm pretty certain that in your 3D printing committee at JSE, you have planned to develop this standardized test method of 3D printed concrete, right? Can you
Yes.
share some information with us using this?
Yes. Yeah. Thank you very much, Dr. Choi. This is very important issue, and we are currently discussing that issue. Yes, and now we are thinking. We try to publish some guideline of the 3D printed concrete, especially focusing on the formwork use. I think that is relatively easy to adopt the 3D printing technology to the reality. Therefore, as a first step, our target is 3D printed formwork, and what kind of design and what kind of construction procedure, what kind of test method is necessary. And I'd like to, yes, publish some standard and guideline. But still, we are discussing this issue with my colleague, and this idea is not endorsed by the chair of the concrete committee. So I'm not sure, but we are planning to work on this line. Thank you very much.
Thank you.
Yeah, we want to have a more discussion. However, it's already over 6 p.m. in Korea, and it's already a very long webinar, more than 3.5 hours. So I think we need to wrap up the webinar. which was very successful. We had a 130 Zoom participants and almost 30 on-site attendees, and now it's already still 100, about 100. But at the peak time, we have more than 160 total, and we are going to ask the speakers whether they are okay to upload this recorded webinar on the YouTube later individually, so that it could be available for everybody. But I know that Professor Ishida will make a presentation in Ryalong not before then, of course, so that his presentation at the Ryalong will be very fresh to that European audience. With that, I'd like to thank all the speakers and audience and discussers, Professor Choi, the president of ACF, to have this great event and pleasant discussion. And it was very informative and very interesting.
I'd like to appreciate all four speakers participating, the experts, student, and of course our excellent moderator, Professor Thomas Kang. Thank you.
Thank you very much. Okay, then we'll see in the next ACF webinar. I don't know whether that's going to be this year or next year, and I hope to meet the speakers in the future.
That depends on you.
Maybe in Korea. Okay. All right. Bye bye then.
Bye-bye.
Thank you. Bye for now.
Bye.